The first method that we use to find the roots of equations is called the graphical method, and this is basically a method that we simply use the graphic of a function, for example here, and wherever the function crosses the x-axis, these dot points, for example, these are the roots of this equation. So graphically we can see them. Basically we make a plot of the function fx equals 0 like this. Then we observe where it crosses the x-axis, and the x values are the approximation of the root. So these estimates can be employed as starting guesses for numerical methods. So this is basically an initial observation of the function behavior, the graphical methods. Not exactly a numerical method, but just an observation of the behavior can be determined. The graphical methods are useful for visualizing the properties of the functions, the behavior of the various numerical methods, as well as anticipating the pitfalls of the numerical methods. With the graphical methods, for example, we can investigate the possibilities of the roots of a function. And for example, depending on the lower and upper bounds of the inputs or variables, xl is the lower and xu are the upper bounds. Depending on these, the function, and depending on the function values, we can have some alternatives. Let's say if the upper bound and lower bound function values are at the same region, or if they have the same sign, there are two possibilities. Here you can see there are no roots because lower and upper are not crossing the x-axis. Basically, we will have a root when the function crosses the x-axis like this. Here it doesn't crosses the x-axis. That's why there is no root. In here also the function values are on the same side, or on the have the same sign, let's say. But this time the function crosses the x-axis twice because it goes down and goes up. That's why it changes the sign twice. That's why we will have an even number of roots. So this can exist in other places as well. That's why we call it not only twice but even. It can be 4 times, 6 times. So no root means 0, and 0, 2, 4, 6 are the root options when we have the same sign of the function values at the lower and upper bounds. The other alternatives exist when the lower and upper bound function values have the different signs. You can see here the lower bound is in the negative. This is the function value is on the negative side for this, and the upper bound is on the positive side. And the function, it means the function crosses the x-axis only once, for example here, but it can also cross more than one, like this. You can see this is on the positive side, this is on the negative side, but in between it crosses multiple times. So in this case there is an odd number of roots exist. Here single, only one root, which is an odd number again. Here 3 roots, again an odd number. So these are the general behaviors of the functions graphically. There are also other root possibilities. For example, here again there is a different sign of the lower and upper bounds, but there seems to be 2 roots only. Actually here we only have a tangential root, let's say. The function simply just tangential to the x-axis, not crossing and passing to the other side. It's just tangentially moving upward again, and that's why here there is 2 same roots. Let's say here, for example, x minus 2, x minus 2, and x minus 4. These x minus 2 and x minus 2 have the same 2 x equals 2 value, which makes this function 0 basically, and it is multiple roots but the same root, so it is tangential. So when we have a function with a tangent on the x-axis, that means at that point there is 2 roots but they are the same. So these kind of methods, to solve them, we will talk about how to solve them in chapter 6, and these are not solvable, or not the chapter 5 methods are not applicable to those. So there are also discontinuous functions. Here also there is a sign change, but because function is not continuous, this is a partial and this is a partial function parts. There can be even number of roots. For example, here two number of roots. Here there is no root, and special strategies are required for determining the roots for these cases. So in chapter 5 and chapter 6, the root types that we use, the numerical methods, are for the functions which are continuous actually, and for the discontinuous functions special strategies are required, and for now we are not seeing them. We will be solving continuous functions in chapter 5 and chapter 6. Now we will have an example to show the graphical approach to find the roots of an equation, and basically we will solve the parachutist example. And earlier, for the explaining the implicit functions, we mentioned that the coefficient c in this equation is actually cannot be isolated. That's why this is an implicit equation, and we need the numerical methods to be able to solve this equation for c. And here we want to solve c as an example using the graphical approach. So for that, what we need to do is basically we will use these parameter values. We know them, just substitute them into here, and for different c values we will check the function values and draw the graph. Then from the graph we will check where it crosses the x-axis. Then we will find the root location of c. So for that, let's work on finding the function values. But before that, let's write the function with the known parameter values. This fc is simply g times m, and g is 9.81, times m is 68.1, divided by c, and we don't know c. And 1 minus exponential, we don't know c, divided by 68.1, times t is 10 seconds, as it is mentioned here. And also there is the velocity. Let me close the parentheses. Then the velocity is 40. It was mentioned here. So if we simplify this a little bit, the function is equivalent to 68.06 divided by c, and 1 minus exponential minus 0.146843 c, and minus 40. So we want to find the function values by simply substituting some c values. For example, let's start with c is 0. So we cannot start with 0, but we can continue greater than 0, because we know that this is a coefficient, it will be positive at least. And the book started with 4, that's why I start with 4 as well. If c is 4, then f4, simply write 4 here and over here as well. Then the result becomes 34.190. And if c is, I will double it each time. f8 is equivalent to 17.712. If c is 12, f12 is 6.11114. If c is 16, by doubling I meant adding 4 each time to c value, so that we will have these values. f12 16 is equivalent to minus 2.230. You can see from 12 to 16 we see a sign change actually, so it seems like it crosses the x-axis. So in between this there can be a root for c, so c can be between 12 and 16. So let's continue. Lastly, 20, and f20 is simply minus 8.368. So these are the values. Let's try to draw the graph of this function using these values. And I will plot the graph on the right hand side. Let's write here like a graph like this, maybe like this. This is FC and this is C. So we know that C's are 4, 8, 12, 16 and 20. These are the values that we used on the left hand side, and the function values are, let me divide this part as 40, 20, 10, 30 and minus 10. So for C is 4, the value is, you can see, 34, which is about here, 34. For 8, it's 17. For 12, it's 6. And for 16, it's minus 2. And finally for 20, it's minus 8, somewhere here. Like this. And if I combine these, there is a somehow parabolic curve, you can see. To be able to have a better curve drawing, you can increase the number of C values. In between these, you can add some values as well, and you can have a better prediction of it. But for now, this is enough to see the root where it is. You can see our root is somewhere here. So this is the root. Graphically, we can determine it. It's about, maybe we can say 16 or 16.5, something like that. Or actually, I said it wrong. So this is 12. This is 16 actually, because I couldn't see it here. I made it wrong. It's below 16. So root can be like 14 or something. 14.5, 14.75. Let's say 14.75. So this is just approximation. But we know that it's crossing the C axis or X axis. How do we determine if this is true or not? We can simply put this into here to see and find the FC value. If FC is 0 exactly, then this is for sure the root. But if it is different from the 0 value, we will see the error. So if we write it down, C is 14.75, then F 14.75 is equivalent to 0.1. So this is very close to 0, but we are slightly far away from 0. Then this is actually, we can say, this is about the root value. So if 0.1 is good enough for us, which is actually good enough, we can say this is the root. But if we think that we need a further refinement of the error, this is kind of the error actually, we need to change this value, maybe 14.7 or 14.8, and try again to get to see how this changes. Whenever it gets closer to 0, that means we are getting closer to the correct root, better and better. So we can use graphical approach this way simply to find the root approximation. In this slide, we have another example. And for this example, we will use the computer codes to plot the graphics and refine the solution to find the root of this equation. You can see this has sinus 10x plus cosine 3x, and we want to find the roots in the range of 0 and 5. So simply, the software packages such as Excel and MATLAB can be used, and in this course we are using MATLAB. So let's say if we want to use MATLAB, simply what we do is for different x values in between 0 and 5, we will find the function values by replacing them here. And on the left hand side, you can see between 0 and 5, we draw the plot of the function. As you can see here, there are many roots actually. It's very like oscillating. Whenever it crosses the 0, there are roots here, 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 here. All of these are roots. And there are also tangential roots. For example, here there's a tangent and it is at 4.2. So tangent means there's double roots over here. And it's between 0 and 5. So what we need to do is from here we can just estimate, for example, around, let me see if this is 1, 2.2, 1.5, 1 is this, 0.5 is this. So around 0.5 we have two roots, around 1 we have root, 1.5 we have two roots, around 2 we have a root, around 2.5 we have two roots, but it's very approximate, we cannot be exact. What we need to do is we need to narrow down our range. For example, here we have a plot of the range between 3 and 5 instead of 0 and 5, and so that we can get closer to see the roots, as you can see. So what we see here is a tangent, and we have a more detailed smaller region so that we can be sure about the position. We can further narrow it down, for example between 0.2 and 0.3, because we said there's a double root. You can see that it actually crosses the x-axis like this. So here, for example, we actually write some x values between 0.2 and 0.3, very small increments, and find the function values again, and then draw this between 0.2 and 0.3. And there are two roots, as you can see, which are about 0.23 and 0.26. And with this kind of closing up is possible with the software. We can simply get the plots and use them to predict the roots easily using the power of the computers.